Welcome to the Deep Dive. We're the place that takes these huge piles of technical docs, all the research, the training manuals, and boils it all down.
Yeah, down to just the handful of insights you really need to know to, well, operate at your best.
And today, we are really getting under the hood of modern financial analysis.
We are. We're looking at how top FP&A teams are mastering SQL and that cloud data warehouse giant, AWS Redshift.
Right, how they use it to build reporting that's repeatable, fast, and crucially trustworthy.
Exactly.
Because if you're at FP&A, you know the drill. You need solid, fast insights all the time.
Monthly recurring revenue, portfolio trends, those KPI dashboards everyone wants yesterday.
But you're pulling from these massive data sets, right? Sometimes decades of historical transactions.
Huge amounts of data.
So our mission today is to cut through all that complexity. We want to pull out the vital nuggets about architecture, modeling, best practices, everything you need to go from analyst to maybe data automation pro.
And that journey, it really starts and ends with SQL, structured query language.
The absolute foundation.
It's basically the universal language for getting data, shaping it, adding it up. If you're figuring out complex delinquency rates or forecasting revenue across, I don't know, 5 segments.
Just SQL is how you do it.
SQL, how you talk to the numbers, yeah.
Okay, so before we even get into the deep architecture stuff, let's kick off with a really fundamental tip. Something straight from these materials about development.
Yes. Start small. Always.
Always start small when writing a new query. Tell us about that.
It's what we call minimal execution. You start your development with the simplest select statement you can think of and immediately add limit 100 at the end.
It seems almost too basic, right? But why is it so non-negotiable? I've seen people waste like half an hour waiting for a query only to see it fail because they skipped this.
Because you save yourself so much pain, and honestly, often compute costs too. You don't want to wait 5 minutes for a full table scan just to find out you, I don't know, misspelled a column name.
Or use the wrong table alias. Been there.
Exactly. Start small, check your columns, check the data types really fast, then you build it up. It just cuts down that feedback loop massively.
Okay, that makes perfect sense. Right, let's unpack the engine room then. AWS Redshift.
The powerhouse.
For listeners maybe coming from desktop tools or, smaller row-based databases, what is Redshift fundamentally, and why is it better for FP&A dealing with all this historical data?
Okay, so Redshift is different because it's a cloud data warehouse built specifically for analytical processing, OLAP.
OLAP.
Okay. It's not tuned for, running a cash register with lots of tiny transactions. It's built for running these big, complex aggregations over lots of data. That focus is key.
And its speed comes down to a couple of architectural tricks, doesn't it? Columnar storage.
That's the first one, yeah. Traditional databases store data row by row. If you have 50 columns, it reads all 50.
Right.
Redshift stores data by column. So if your query only needs, say, transaction date and revenue amount,
It just reads those two.
it literally ignores all the other columns, only scans the 2 it needs. That makes aggregation incredibly faster.
Wow, okay. And the second part, massively parallel processing, MPP.
Exactly. So you take that efficient column scan, and then MPP kicks in. There's a leader node that parses your SQL.
Sort of the traffic cop.
Kinda, yeah. It figures out the plan. But
Okay.
the actual hard work, the scanning, the filtering, the joining millions of rows that gets distributed across potentially dozens, even hundreds of compute nodes,
All working at the same time.
all running in parallel. It's like one person trying to move a mountain of files versus having a whole team doing it simultaneously.
That sounds perfect for FP&A since we're almost always summing up history. But the sources did flag a warning here. Something analysts can miss.
Yes, this is a really important caveat. Redshift is brilliant for aggregating millions, even billions of rows. But if your main job is doing constant, small, single-row lookups, like checking one customer status right now,
You might actually be fighting the system.
you might be. It's not optimized for that high-frequency, low-data volume query. You, as the analyst, need to think in terms of bulk operations. That's where it shines.
Got it. Bulk reads, not tiny writes or lookups.
Yeah.
Okay, so how do we control performance? The materials talk about distribution keys and sort keys. How do they help organize the data?
They're both super important for telling Redshift how to arrange the data physically for speed.
Which one matters more for typical financial reports?
Well, distribution keys, often set to key, are mostly about optimizing joins. You distribute your big tables, like transactions and customers, on their common join key, maybe customered.
So matching data lives on the same compute node,
Yeah,
reduces data shuffling.
exactly. Less data movement during joins. But for FP&A reporting, sort keys. Sort keys are often the secret weapon.
Okay, why?
Sort keys dictate the physical order the rows are stored in on disk within each node. Now think about how you filter financial reports.
Last month, last quarter, year to date. Always by date ranges.
Precisely. If you define your main date columns, transaction a day, reporting period, whatever, as your sort keys,
Redshift can use that order.
it can skip huge blocks of data that fall outside your date range. It doesn't even need to read them. If your table isn't sorted by date, Redshift has to scan way more data, maybe everything, just to find the rows for last quarter.
Ah, so a massive performance gain just from sorting correctly. That's a great practical tip. Date fields are usually your best bet for sort keys in finance.
Almost always, yes.
Okay, so we understand the engine, but even a great engine needs a well-designed car around it. Let's talk data modeling, structuring the financial world inside Redshift. The standard seems to be the star schema.
Yes, the star schema is kind of the go-to for analytics. You have your fact table right in the middle.
That holds the numbers, revenue, units, payments.
Exactly, the quantitative measures plus keys to link outwards. And around it, you have your dimension tables.
Which give context. Product names, customer details, date attributes.
All the who, what, where, when, product, customer, geography, time dimensions. It's simple and optimized for reporting queries.
Now, the sources also mention the Snowflake schema. It sounds tidier, maybe? More normalized? Dimensions branching off dimensions?
It is more normalized technically, like a customer dimension might link to a separate geography dimension.
So why do the materials strongly suggest FP&A teams should prefer the star schema, especially in Redshift? Seems counterintuitive if Snowflake is cleaner.
Because remember, Redshift is OLAP optimized for reading lots of data quickly for analysis. In OLAP, query speed almost always trumps slight storage savings.
And Snowflake means more joins.
Yes, more joins mean more complexity and potentially more latency, even on a fast system like Redshift. The star schema usually means fewer joins in your typical reporting query. You keep the dimensions slightly less normalized, maybe repeat some attributes, but the queries are simpler and faster. Redshift's compression often negates the storage benefits of extreme normalization anyway.
Okay, stick with the star for simplicity and speed in Redshift. But speaking of normalization, even in a star schema, getting the basics right is crucial for data integrity, right?
Yeah.
Tell us why that matters so much in FP&A.
Oh, absolutely critical. Normalization is what ensures your metrics are actually accurate and consistent over time. Let's take an example. Imagine you stored, say, the customer's current sales segment directly in every single transaction row they ever made.
Okay.
Now, what happens 6 months later when that customer gets reassigned to a new sales segment?
Uh-oh. You'd have to find and update potentially millions of old transaction records just to change the segment history.
Exactly. It's a nightmare. It's slow, error-prone. By normalizing, you separate that volatile attribute, the sales segment, into the customer dimension table.
So it lives in one place.
Right. When the segment changes, you update one row in the dimension table. And boom, all historical reports that join to that dimension instantly reflect the correct segment for the right time period, or just the latest segment, depending on how you model time. It prevents those historical inconsistencies, guarantees accuracy.
That makes total sense. Avoids polluting history.
But you mentioned denormalization earlier. Sometimes we do want less normalization. When do we break the rules?
You break them strategically, usually only in the data warehouse layer itself, and almost always purely for performance or sometimes readability.
Like pre-calculating complex metrics.
Precisely. If you have a really complex calculation, maybe monthly recurring revenue with lots of rules and it gets queried constantly, you might pre-aggregate it. You calculate it once, maybe daily or hourly, and store the result in a summary table or a materialized view.
So you trade off the calculation cost for faster read speed.
Exactly. You denormalize by pre-calculating, but you do it consciously, knowing the trade-offs. Got it. Okay, let's shift gears to the analyst actually using this stuff. Day one, you log into a new Redshift cluster. Could be hundreds of schemas, thousands of tables. Where do you even start finding the data you need? What's the workflow?
Yeah, it can be overwhelming. You need a systematic approach, basically using SQL to explore the database's own metadata, its data dictionary,
Like a map.
like a map. First, you list the available schemas, see what different areas exist, then pick a schema that looks relevant, like finance or sales, and list the tables within it. Views like SPV table info are great here, and you can order by table size. Bigger tables are often more important.
Find the big fact tables first.
Usually, yeah. Then, once you have a promising table, you explore its columns and their data types using something like information schema.columns. It's like a funnel, .schemas, then tables, then columns.
And a pro tip from the sources. Start exploring in read-only schemas if possible.
Absolutely. Protects you from accidentally changing anything in production while you're just looking around. Safety first.
Okay, so you found some tables, but you're not just looking at columns, right? You need to check the health of those tables.
That's crucial for performance. You use those same dictionary views, like SVV table info, to look for red flags. Two big ones are stats off and unsorted.
What do they mean?
Stats off tells you the percentage of table data that's changed since Redshift last analyzed its statistics. If statistics are stale, Redshift's query planner can't make smart choices, and queries slow down.
And unsorted.
That relates to your sort keys. It shows the percentage of rows that are out of physical sort order. If that's high, your sort keys aren't effective, and Redshift is reading way more data blocks than it should.
So if stats off is over, say, 10% or unsorted is over 20%.
Yeah, those are rough guidelines from the material. If they're high, it's a strong signal you probably need to run analyze-z to update statistics and VACUM to resort the data physically. Housekeeping, basically.
Makes sense. Clean house for better performance. Now let's get into actual exploratory data analysis, EDATE, with SQL. We're running basic checks counts, min, max, averages. There's a neat speed tip here for big tables.
Yes, for distinct counts on really large data sets, instead of count, distinct column name, try using approximate count, distinct column name.
Approximate. That sounds risky for finance.
Well, here's the thing. It's very close, usually within about 2% accuracy according to the Redshift docs, but it runs dramatically faster, like 10 to 15 times faster.
Okay, but I have to push back a bit. If I'm doing official reporting gap numbers for the board, I can't use an approximate count, surely.
Absolutely not. You draw the line based on the use case. Official reporting, final metrics for external stakeholders. You need the exact, precise count distinct, no question.
But for quick exploration.
But if you're just trying to get a feel for the data, like roughly how many unique customer IDs are in this 5-year transaction table, just for your own understanding during analysis, approximate count is perfect. It gives you a fast, directional sense. It's a profiling tool, not necessarily a final reporting metric tool.
Okay, understood. Use case dictates precision. What about quick quality checks? Finding anomalies with SQL.
This is where case when combined with aggregation functions like count or sum is really powerful.
How so?
You can write a query that instantly counts potential problems, like count case when transaction amount is null then one end, tells you how many nulls you have. Or sum case when transaction amount 0 then one else 0 end, counts negative amounts.
Or future dated transactions.
Exactly. Count case when transaction get date then one end. You can check multiple conditions in one pass. Super useful. You can also use functions like with bucket to see how values are distributed across ranges, great for spotting unusual concentrations or outliers.
And one final point on EDA, time consistency.
Oh yes, crucial. When you're filtering data for time periods like last 12 months or this quarter versus last quarter, always use functions like dateTrendC consistently.
To align the start and end points properly.
Precisely. dateTrendC month, date column, snaps any date to the first of its month. Using this ensures you're always comparing exactly equivalent time windows. It prevents subtle errors in variance analysis just because one period accidentally started mid-month.
Good discipline. Okay, that leads us nicely into segment 4, advanced query logic. We have to talk about joins, the glue that connects our data.
The absolute workhorse. We use joins constantly to enrich our fact tables with descriptive attributes from our dimension tables. A classic example is a left join from a payments table to a customers table to add the customer's segment or region to each payment record.
Standard stuff. But this is where the materials issue a very serious warning. Probably the single most dangerous mistake an FP&A analyst can make in SQL.
Without a doubt. It's unintended row multiplication.
Sounds bad. What is it?
It's when you join two tables, say, transactions to customer details, but Your join condition, or the data itself, creates a one-to-many relationship where you didn't expect one. Maybe a customer accidentally has 2 active records in the dimension table.
So the join creates duplicate transaction rows.
Exactly. You might join a transaction table with 1 million rows to a dimension, and suddenly your result set has 1.1 million rows. Those extra 100,000 rows are duplicates.
And you then sum up revenue.
Your total revenue is suddenly inflated. It could be doubled, tripled, completely wrong. And if that number goes into a report, especially to leadership, well, it's a potential catastrophe for credibility.
Okay, nightmare scenario.
Yeah.
How do we prevent this? Absolutely, 100% prevent it.
Verification. Constant, rigorous verification. After every join where you plan to do aggregation, SUM, AVG, etc., you must check your row counts.
Okay.
Run 2 counts on your joined result set before you aggregate. Check count, the total number of rows, then check count, distinct primary key of the mainable.
Count the unique keys from your starting table.
Yes. If those 2 counts don't match exactly, your join has introduced duplicates. You have to stop, figure out why, and fix your join logic or clean up the dimension data. Do not proceed with aggregation until those counts match.
That is potentially career-saving advice right there. Check count versus distance after joins.
Memorize it. Live by it.
Okay. So once we've mastered safe joins, the next hurdle is often complexity. Financial calculations can involve many steps, multiple tables. This brings us to CTEs common table expressions, the with clause.
CTEs are, I'd say, the mark of clean, professional, maintainable SQL, especially for complex analysis.
Why are they so much better than, say, deeply nested subqueries?
Readability and modularity. CTEs let you break down a really complex piece of logic into named, sequential, temporary steps. You build the query layer by layer.
The materials used a good example, a retail account snapshot query. Joining accounts, financials, customer geography, delinquency status. Sounds complicated.
Right. Imagine trying to write that as one giant query without CTEs.
A monster query.
A monster. You'd have this enormous select list, conditions repeated everywhere, business logic buried deep inside nested parentheses. It would be hundreds, maybe thousands of lines long, utterly terrifying to debug or modify later. Impossible for a colleague to understand quickly.
Okay, paint the after picture. How do CTEs help?
With CTEs, it becomes structured, you might have, with base accounts as select from Ganswer.
Step 1, get the core accounts.
Then with account financials as select from financials join base accounts.
Step 2, add financial details.
With enriched geography as select from geography join base accounts, and so on. Each CTE builds on the previous one, focusing on one logical step.
You name them clearly.
You name them clearly. Base accounts, monthly revenue, delinquency flags. The code becomes almost self-documenting. You can even test each CTE independently during development. It transforms an unreadable mess into a clear, step-by-step workflow.
That modularity must be huge for collaboration and just making sure the logic is repeatable and correct.
Massive win. And honestly, readability trumps clever but obscure code every single time, especially in a production environment.
Absolutely. Okay, we're heading into the home stretch, finishing strong with best practices and, crucially, automation. Let's quickly recap the core rules for keeping SQL reliable. The KISS principle, maybe?
Keep it simple, right? First, as we started, start small, select plus limit. Filter early in your query using the where clause, don't pull data you don't need. That's the biggest performance gain usually.
Makes sense.
Use meaningful aliases for tables and columns. Use consistent casing. And, as we just discussed with CTEs, prioritize readability over complex, clever logic. Write code for the next person who has to maintain it, possibly you at 2 a.m.
Good advice. Okay, now the big leap, automation. FP&A needs results that are repeatable, timely, consistent, especially for things like monthly reporting closes. This is where Python often comes in.
Yes, Python acts as the bridge. It takes your well-crafted SQL query and turns it into a scheduled automated job.
How does it help with, say, running the same report for different months or different business segments?
Parameterization. Instead of hard-coding October 2025 into your SQL, your Python script calculates the required dates dynamically. It passes these dates, or maybe specific segment IDs, as parameters into the SQL query when it runs.
So the SQL stays generic. The Python script handles the specifics for each run.
Exactly. Makes the whole process flexible and reusable.
But integrating Python and SQL like this raises a huge security flag, doesn't it? Something we absolutely cannot get wrong.
Oh, yes. This is non-negotiable security 101. You never, ever build your SQL query by just concatenating strings together with variables directly directly from Python.
Like SQL, select from table where date plus report date plus wait date.
Never do that. That opens you wide up to SQL injection attacks. Someone could potentially manipulate the input report date variable to run malicious commands on your database.
So what's the safe way?
Always use parameterized queries. Your SQL can has placeholders, often persons, and your Python database library safely substitutes the variable values into those placeholders. The database driver handles the quoting and escaping to prevent injection. Always use parameterization. No exceptions in production code.
Critical point. Okay, finally, reliability. Production jobs fail sometimes, network glitches, database issues. If your monthly reporting script crashes halfway through, you can't leave the main reporting table in a broken, half-updated state, right?
Absolutely not. You need fail-safe workflows. This brings in the concept of idempotent jobs.
Idempotent, meaning?
Meaning the job produces the same end result regardless of how many times you run it. If it runs successfully once, running it a second, third, or fourth time doesn't change the outcome or mess things up.
How do we achieve that for, say, loading the current month's data into a summary table? And insert seems like it would add duplicates if run twice.
Right, so instead of just insert, a common idempotent pattern for loading monthly data is delete plus insert.
Explain that.
Before you insert the data for, say, October 2025, your script first runs a delete statement to remove any existing data for October 2025 from the target table.
So you wipe the slate clean for that specific period first.
Exactly. Then you run your insert to load the fresh data. Now think about failure. If the script fails after the delete but before the insert finishes, what happens when you rerun it?
Well, the delete runs again, maybe deleting nothing this time, and then the insert runs, loading the complete data set for October. You end up correct.
Precisely. The delete plus insert pattern ensures that even if the job fails and needs rerunning, you won't get duplicate data. Your financial totals remain accurate and complete. It makes your production workflow robust and reliable.
That's brilliant. Safe reruns. Okay, let's wrap this deep dive up. We've covered architecture, modeling, querying, automation. What's the bottom line for an FP&A analyst trying to master this modern data stack?
I think it boils down to a few core pillars. Success really hinges on leveraging Redshift's performance, understanding columnar storage, using sort keys smartly. Having robust data models, usually favoring the simplicity of the star schema for analytics.
And the critical checks.
Absolutely critical. Verifying every join result to prevent those catastrophic aggregation errors. And finally, adopting modular logic with CTEs for readable, maintainable, and testable code.
That's a great summary. So here's the final thought, the challenge for you, the listener. The real goal here isn't just about running queries interactively. It's about moving to reliable, scheduled output that runs itself.
Right. Stop focusing only on how to calculate the number manually each month. Start focusing on how to automate its consistent, trustworthy delivery.
So the next step.
Pick one. Just one monthly report you currently pull together by hand, maybe in Excel after running a query, even a simple one. Your task is to replicate its core metrics in one clean, verified SQL query use CTEs. Then, build a small, parameterized Python script that runs that SQL and automatically outputs the result, maybe to a CSV, or even directly into a structured Excel file.
Just doing that one exercise.
That single exercise, end-to-end, will genuinely shift your perspective. It takes you from being primarily a spreadsheet user to someone starting to build reliable data pipelines on a modern platform. That's the leap.